Do you know the real difference between the double equals operator and is? Can you tell when Python is checking for matching values versus a direct memory reference? Mastering this distinction is vital. If you miss this, you'll be lost in Python logic. Let's start with a list. We have a variable which points to a specific list. It's storing data in memory. Think of it like a shopping list. In Python, we define these using square brackets. Imagine you have your list, but someone else say, your partner needs to see it too. What's the move? Do you hand over a physical copy? Or do you both look at the exact same piece of paper in your hand? Where that list is stored makes all the difference. Is it in your pocket while they have a duplicate? Or are you both sharing the same physical object? Python works the exact same way. Let's look at the code. Variable A is assigned these specific items. It's a shopping list containing 1, 2, and 3 items total. B is assigned an identical list, but C is set directly to it. So, what's happening under the hood? If we run an equality test asking is it equal to B, Python checks the contents. Are the items inside listed the same as the items in list B? Do they contain the same data? If your list was bread, eggs, and milk, and their list was also bread, eggs, and milk, they are equal because the values match perfectly. That test passes as true. That is the job of the double equals operator. But then there's is. If we ask, is B, the result is false. You might think, hold on, they have the same numbers. But that's not what this keyword checks. In this scenario, we've actually created two separate lists. A is your list. B is a completely different list for someone else. Even if the items match, they're distinct. You essentially made a separate copy. You have yours, they have theirs. These are two different objects in memory. That's why is returns false. A is not the same entity as B. Now, let's test if is C. Remember, we set C to point directly to A. It doesn't just have the same values, it's looking at the exact same object. It's the same physical list. It's like you holding the list in your hand, and your partner reading off that very same piece of paper. This returns true because A and C are one and the same. Identity check, passed. And if we check a double equals C, it asks, are the items inside matching? Of course they are, because you're looking at the same source. So this is also true. Visualizing this makes it even clearer. Look at our variables, A, B, and C. A points to an object in memory, let's call it object A. B points to a different list entirely, even with the same brackets and the same data. It's a fresh instance. This is a brand new entity, object B. But notice C is pointing directly to object A. It's an alias. Look at it this way. In this diagram, A and C both point to that one list in your hand. They are sharing the same memory address. Meanwhile, B went off and created its own separate copy. B has its own unique space. This is how the computer manages your data. A and C reference one memory location. They are identical. They point to the same spot. But B is pointing somewhere else entirely. It's a separate list even if the items look the same. These two lines of code look fine, right? Wrong. They're facing a massive identity crisis. Whenever Python runs, it creates objects in your memory. This specific block here, that's an object. Specifically, it's a dictionary. Now, watch this. We're defining a second variable called backup configuration. Imagine you have a server and you're storing its user preferences inside this configuration variable for easy access. Naturally, you want your users to be able to change their settings, but also have the option to revert if they make a mistake. So, you create a backup. At first glance, this code looks totally reasonable for saving that state. If we check if the configuration is equal to the backup, Python tells us, true, they both hold the exact same data. Perfect, right? But here's the trap. If a user changes a value in the original, that change instantly overwrites your backup too. Why? Because they are both pointing to the same object in memory. That is exactly what this operator is revealing here. What you actually needed was a completely independent copy. To fix this, we use the copy method. And pay attention here, you must include the parentheses at the end. If you forget them and just type .copy, the variables won't behave like you expect. Without parentheses, you're just looking at the memory address of the function. The code doesn't actually run a copy command unless those brackets are there. This is a golden rule. Always use parentheses to execute your methods. Now watch the magic. When we ask Python if the configuration is the backup configuration, are they the same physical object? The answer is finally false. Remember, without that copy method, the result is always true because they're sharing the same space in your computer's memory. By using copy, you create two separate, independent objects. Avoid this pitfall and your data stays safe. Identity operators are incredibly powerful when managing large data objects. They allow you to efficiently detect if your code is using a cached version of an object or if it's interacting with the live data directly. Imagine you were pulling thousands of records at once. In this specific example, our dictionary object is small. You can identify it as a dictionary by these curly braces. Inside, we have a key, where the associated value is actually a list of items. Now, imagine scaling this up to thousands or even millions of entries. Attempting to create a full copy in memory would cause a massive performance hit. To solve this, we use a variable called cache that we pass into a method. Instead of duplicating the data, we simply pass a reference to the existing object. Think of it like a long shopping list with 100 different items. Rather than rewriting that entire list from scratch, you'd rather have the other person look at your original list. You might take a quick photo and send it over, ensuring you are both referencing the exact same information. So, here our data is cached. We are checking if this variable points to the exact same object in memory. This is the identity check, and it is a vital tool for performance. If you actually needed a duplicate, you would use the copy function like this. When we run this method, you'll see that they become two entirely different objects. Now it's occupying more memory than it strictly needs to. Identity operators are also great for managing user sessions. If a user starts a session on your web app, you need to know, is this a new session or an existing one? If it's a brand new session, this identity operator will verify that. It would report that these two are not the same. However, if it's the same session being continued, the check returns true. But if the user starts a completely separate session, even though it's the same user, they are in a different session object. In this case, the identity check is false, but is the user the same? If the user data matches the values we expect, the equality check returns true. Always remember the difference between is and equals. I'll bet you've wondered about the real difference between none, empty strings, and empty lists. What about empty dictionaries or zero values? In this breakdown, we're going to master exactly what the none type represents in Python. Imagine you have a function designed to search through a user database. Right here, we've built a hard-coded dictionary to simulate that database. It contains records for John and Bob, along with their specific email addresses. When we trigger this function, its job is straightforward. It retrieves and returns the user's email. The database.get method looks for the unique key and pulls the corresponding email straight from our dictionary. But what if you search for a user who isn't there? Look closely. There is no Charlie in this dataset. Because he's missing, Python returns a none type. Let's run the code and see. There it is. The email is none. When the search for Charlie hits the database, the system confirms the record simply does not exist. None represents a total absence. It's the ultimate placeholder for nothingness. It is a void. Total silence. It's not just empty, it's non-existent. It isn't even an empty string. Let me prove the difference to you. If I change the search back to Bob, who we know is in our database, and execute the code, we successfully retrieve Bob's email. Now, watch this. If I replace Bob's actual email with an empty string, what do you think happens? Will it say not found, or will it actually print that empty space? Let's find out. The console just printed a blank line. The program successfully found the empty email address. It exists, but it contains 0 characters. It's just empty. This distinction is vital. None means there is no value at all. An empty string is still a string. An empty list is still a list. An empty dictionary is still a dictionary. None of these are the same as none. That's the key takeaway. As we just saw, an empty string is definitely not equal to none. Bob exists in our system. His record was found, even if the data was just a blank string. See? We received an empty string back, rather than a none value. However, if I search for Bob1 who isn't in our list, it triggers our user email not found logic. That line only prints because the none criteria was met. In short, none means nothing is there. If you get a result, it means something was found, even if that something is empty. In this specific case, it was an empty string. Plain, simple, and empty. Mastering the difference between none and an empty string is vital. In the world of Python, getting this wrong can stall your progress instantly. Avoid the common beginner pitfalls by understanding this core concept. Let's dive into why these two values are not the same. Look at our variables. A is assigned to none, and b is an empty string. When we run a comparison to see if A equals B, what happens? The result is false. Even though they both look empty, they are fundamentally different. Variable A represents nothingness, while B is a container that is simply empty. In Python, none signifies a completely missing value. Let's break this down with a practical analogy you'll never forget. An empty string is defined by quotation marks with absolutely nothing inside. There isn't even a space character, it is a defined but empty piece of data. That is the technical definition of an empty string. Now, consider an empty list, which we represent with square brackets. Think of it like a shopping list on a blank piece of paper. The paper exists, but it has no items on it. You are holding the paper in your hand. It is a physical object. However, the list itself is blank. The container is there, but the content is 0. Compare that to none, which is like having no paper at all. One is an empty container. The other is the total absence of a container. If you compare no paper to a blank paper, they aren't equal, right? It's the same logic for none versus an empty string or list. Think of it like an exam. An empty string is turning up but writing nothing. You handed in the paper, but it's blank. You were present. But none means you didn't even show up to the exam hall. You were absent. The exam paper for you doesn't even exist. We can verify this by checking the data types in our code. When we check the type of A, we see it belongs to the none type class. This is a special designation in Python that confirms the value is missing. It means the data is absent, you went completely off the grid. An empty string, however, is still a string type. You were there, but silent. That is the best way to remember it. None is being absent from the room. An empty string is being in the room, but staying completely quiet. The none type class proves you weren't on the guest list at all. One represents empty, while the other represents nothingness. Master this distinction, and you'll write much cleaner, bug-free code. Ever wondered how to check for an empty list? Most people get it wrong. There is a professional standard, and several ways to approach it. Let's master the proper method. This is the cleanest way to verify a list. Looking at the screen, we have an empty list defined with nothing inside. It is completely blank. We use an if not condition. While not might seem confusing at first, it is incredibly powerful. Let's break it down. Items is our variable name. The not keyword in Python effectively checks if the list is empty. When the list has no elements, the empty message is triggered. Running this code confirms it. The logic executes because the list is void. But watch what happens when we add data. Let's add eggs to the list. Now the list contains one item. The output changes instantly to show the list has data. This if not style is what developers at Microsoft and Google use. It is the industry standard. What is the alternative? You could take a beginner-friendly route. Some beginners check the actual length of the list. If the length equals 0, the list is empty. While this works, it's considered an entry-level approach. Pro software engineers usually avoid this. The elite teams at Facebook and Google skip this method entirely. Avoid it if you can. It adds visual clarity, sure. But it's not the most efficient way. Truthfully, it's just extra code. Stick to the professional method instead. Now, do you always need the not keyword? Not necessarily. You can check for the presence of data directly. By removing not, we can simply say if items. This looks for any content within the list. There we go. We just swap the logic. Now, list has data becomes the primary check. If it contains anything, the first block runs. Otherwise, it falls through to the else block. Simple and clean. You have total flexibility here. You could also compare it directly to two empty brackets. But again, this is frowned upon in professional circles. I'm showing you this so you recognize it, if you ever see it in production code. Finally, let's look at a real-world example. Imagine a list of customer orders. If there are no orders, we want to print no orders to process. As you see, the script handles the empty state perfectly. This is the preferred approach. Whether you use the not keyword or not, just ensure your logic matches your goal. Choose the one that makes your code the most readable. Now you know how to handle this like a pro. That is the true Pythonic way of coding. The Pythonic way to check for an empty list is simple. Just write if not items. Now, this syntax might look a bit strange at first glance, and you might wonder how it works. Don't worry, it all comes down to a powerful concept called Falsy values. So, what exactly are these values, and how do they help us detect an empty list? Let's dive in and take a closer look. Python classifies specific objects as falsy. This list includes none, the actual Boolean false, and the number 0. It also covers floats like 0.0, empty strings, empty lists, and empty dictionaries. Even an empty set is considered falsy. These are all treated as false in logic tests. Looking back at our code, when we use the not keyword, we are essentially checking if the list is empty. If it is, the condition becomes true. You could also write this without the not. But you'll need to swap your logic. Let's move this block of code around to demonstrate. We'll shift this up and the other down. Now, if items checks if the list has content. Since it's empty, it evaluates to false. The code will skip to our else output. It detects the false value and prints the result. Adding not simply flips that logic right back around. Both methods work, but one is much cleaner. Falsy values are the secret sauce here. As mentioned, empty strings work the exact same way. If we run this, our current label might say the list is empty. But technically, it's the variable itself that is empty. An empty string is just another falsy value. Keep that falsy list in mind. It covers strings, zeros, the Boolean false and none. Let's prove it with some quick tests. Take this empty list. When we convert it to a Boolean, the output clearly shows false. But if we add some data like eggs into the list, it instantly becomes true because it's no longer empty. Same for our strings. An empty string is false. But as soon as we type a character, it flips to true. Here's a real-world scenario you'll see often. Imagine an API that returns an empty list. You can easily trigger a no results found message using this logic. The not keyword handles the conversion automatically. It's just checking the truthiness of the object. Simple and effective. Try it with an empty string, and you get false. If that result isn't true, our code executes. I hope this demystifies falsy values and the strange way Python handles empty lists. Now you know exactly why this code works. Ready for the next step? We previously saw how to validate if an empty list contains any values. An if statement effectively checks whether that list is empty or not. If you missed how that works, definitely check out my previous videos. Essentially, every object evaluates to either true or false. As you know, if statements rely entirely on these Boolean checks. Python converts an empty list to false. These are known as falsy values. They are a fundamental part of mastering Python logic. Think of none, the false keyword, the number 0, and the point of. Empty strings, lists, dictionaries, and sets all belong to this group. Internally, Python treats every one of these as false. Let's look at how the list item specifically works. How does Python actually perform this conversion behind the scenes? Python executes a specific order of operations to find the truth. First, it checks the type. If it's already a Boolean, like true or false, it simply returns that value exactly as it is. No extra work needed. Supply false and you get false. Supply true and you get true. But what if the type isn't a Boolean? Like our empty list over here? If the object is not a Boolean, Python moves to the next logical step. It doesn't just give up. It looks for another way to measure truth. This is where the length check comes into play. Python asks, does this object have a length? If it's not a Boolean, it calls the internal len function to see what's inside. If the length is 0, it's false. Otherwise, it's true. It's that simple. So, check for Boolean first. If not, check if the length is 0. If the length equals 0, the result is false. But if the length is 1, 2, or 3, that becomes a truthy value. Watch, when we check the length of this empty list, the output is 0. And when you cast that to a Boolean, you can see it returns false. 0 items means a false evaluation in Python logic. But look what happens when we add items. I've added 2 items here, and it immediately converts to true, because the length is no longer 0. Let's dive back into Python's truthiness and those tricky falsy values. Our classic example for this is the empty list. Ever wonder why a simple if item statement actually works? What's happening under the hood? Essentially, an empty list is automatically treated as false. But as soon as you add an item, for example, the letter A, the entire list is converted to true. Empty equals false. Items equal true. Simple, right? That's why this logic is so powerful. But here is the best part. You can control this behavior. Internally, Python examines every object you throw at it. It asks, does this object belong to the Boolean class? If it does, it simply returns true or false. If not, it calls a hidden method called the length method. This method lies in every class. If the length is 0, it returns false. Otherwise, it returns true. It's a built-in rule. Now, look at our custom shopping cart class. Imagine you're designing your own application. You have a cart filled with shopping items. We can actually override that hidden length function to return whatever custom value we want. We are taking full control of the default logic. Even if the cart has 0 items, we're going to force it to add 1 to the result. We want Python to think the cart is never empty. Watch how this changes the outcome. Now, when we run the code, even though it says the cart is technically empty, it's not treated as empty, just by adding that single-digit 1. That's why this code works. If we remove that line or set it back to 0, the cart is empty message returns because the length is back to 0. The cart is officially empty once again. A standard empty cart. This is exactly how Python works. It calls the length function. If length equals 0, it's false. If not, it's true. By faking the count, we completely control the truth. We just add 1, and boom, the object is evaluated as a true value. And your code executes exactly how you planned.